And I'll now invite Professor Tropea to begin his talk.
Just need a microphone. Okay, thanks a lot. And I also thank, of course, our chairman and organizer of the conference. Very pleased to be here. And actually, he didn't mention, I am not Stefan Hart, so, and I cannot replace Stefan Hart. So I'm a little tangential to what was just talked about in the last talks. I think it probably fits better on Sunday. Nevertheless, it basically fits under the heading of wetting and microfluidics, and I'm going to talk about dynamic capillary rivulet rise on real-world corners. And actually, the person who did all the work is Felix Gerlach. He was a PhD student, finished some years ago, and most of what I talk about is from his dissertation. Okay, so basically, we're looking at capillary-driven flows under gravity, force of gravity, and this is rather important. And I said real world, and it's rather important in a lot of applications, and of course the main one is coding and dip coding, etc. Because there you have not exactly 90-degree corners, but something with some curvature within the corners. So that's where you say real world corners, and also roughness, by the way. So this is, has lots of applications, dip coding, and the question is, do things change from the ideal case? And I mean, these are complex geometries, and if we want to make any headway, we have to simplify things into something generic. And the generic idea was, okay, this is looked at quite often, this kind of capillary rise in cuvettes, and what we've chosen is the following: capillary rise in basically an inner and an outer corner, and we've made them 90 degrees, while 270 degrees in both cases. So we have one inner and one outer corner, and just for the vocabulary here, we'll call that the rivulet and that the cusp. So when it's going down, that's the cusp, and going up is the rivulet. And I think that's normal, and most of you know about that. So we started actually experimentally, and then we said, okay, we have lots of observation, then we have to say, okay, can we model that? And so most of the actually all of the experiments I'll show today are this geometry. We're not always using aluminum, sometimes steel and sometimes plastic. It depends on the conditions, the wetting conditions we want to achieve, but and almost always silicone oil. But it's fairly simple geometry, but now we come, and I show a little bit here now the details of the rivulet and the cusp. Okay, and as you can imagine, the contact angle plays a big role here. And so we can look at different contact angles like this, and like this. And you see, you can already see here we have convex, concave, and straight. And it all depends a little bit on the opening angle gamma of your corner. And we're using 90 degrees. But what I'm going to do in modeling and whatnot is not restricted to the 90 degrees. And then the Congas-Finn criterion basically says, okay, will you get concave or convex or straight? So in this case, 45 degrees is the limiting factor. And a lot of work has been done, and one of the main authors of that work is sitting in front of me. And they've basically looked at the case of, in this theta less than 45 degrees. That would be the ideal case for rivulet rise. And that comes, of course, the 1/3 comes, of course, from David and co. And that's the normal, ideal 90-degree case. And it goes to infinity. So the rivulet goes up to infinity, never stops, and the time at which it takes to go to infinity and the time evolution is well described. But we want to look at real world, not 90 degrees. There's some, it doesn't matter how you make it, there's some curvature in there. And the question is, how does that? So, and one of the difficulties, this is not a trivial experiment for two reasons. And one of the difficulties is the following. Oh, sorry, went too fast. I've tried to show it here. So you look at this specimen, which is our 90 inner outer corner, and it goes into some liquid pool. And we're going to look at three cases. And one of them is that we're dipping in at a constant rate. And you have the problem that if you dip it in a constant rate and you start going faster, then you need a big specimen and a big pool. Otherwise, it never gets into a steady state case. It's not an easy experiment to build. I can tell you that while it was a dissertation. So, okay. So that's what it looks like, and you can see the pool is rather deep, because when you first dip in, it's not yet steady state, and when you start going faster, well, at some constant speed, it takes a while before you get this steady state condition. The other problem is, of course, that you're looking from outside into a containment with a different refractive index, so you have some distortion. And not only that, it's difficult, it's a three-dimensional object, and you're looking at a projection, or maybe two projections, and somehow you have to go from a lab fixed into the coordinate system of your system. Okay, this is actually a talk on trigonometry. So you can imagine somebody has to be behind all of this and do the image processing, and we'll come to the rest of the trigonometry later. Okay, but it's not rocket science, but it's not simple either. So this is maybe just 2 or 3 slides about imaging and how you have to go about that. So, you know, you look at something at some angle. You can't look from above. You can't look too much from below. It's not, as I say, an easy experiment. And so you have some targets, and you try and get your 2D projection onto a 3D, and it's a perspective. And of course, you have to use a small aperture so that you have a large depth of field, etc. But in the end, and not only that, you don't get good contrast. It's difficult, even with flash, it's difficult to get good contrast at the contact. So it's very difficult to measure contact angle, which is something you also want to do, at least in the dynamic case. You can do it outside, you know, with a cruise instrument or something, but it's difficult to measure online. And so what you can do is, at most, the contact line. And even then, the contrast is not good, so in the end, you start doing it manually. And so you get some sort of a coordinate system and some projection transfer coordinates to go from your 2D into the 3D. So actually, I'm going to talk about 3 cases, and they're all rather interesting practically. The first case is what happens if now the outer corner gets closer and closer to the inner corner? Does the rivulet influence the cusp, or does the cusp influence the rivulet, or both? That's a question that's actually quite interesting. The second is the real world corner. So it's not exactly 90 degrees, but there's some finite curvature left over. And does that influence then the speed or the infinite rise of the rivulet? And the last case is if you're dipping and you have a velocity going down, what does the rivulet then look like? And you can imagine you've got sort of superimposed the rivulet coming up, and then you're going down. Okay, does it cancel out? And how do we look at that? So this is the type of thing we're looking at. And by the way, I draw your attention, there's a rivulet, a rivulet here and a cusp here. And one thing that I don't have a picture of, but I'd like to explain it now so you can imagine it later on the curves, is if this outer corner gets closer and closer to this rivulet here, so the cusp is getting, then what happens is, you see, the cusp goes down and comes back on the same point. But if you get closer, then it separates, and you get it gets pinned on this corner, so it gets pinned here, and the cusp on this side comes from here. So that's what we're going to call separation of the 2 meniscus on the 2 planes of the cusp. I don't have a good picture of that. I should use that. So now you have to pay attention. These are not easy curves to understand, but this is the result. This is now contours of the rivulet contact line. And I'm showing actually, so again, pay attention. What this is now, for instance, changing. By the way, everything is dimensionless with the capillary length. No? So like if the inner corner here, that's the rivulet going up, that's the contour. If the inner corner is 10 capillary lengths away from the cusp, you see that's the cusp, then you have the cusp, then basically you have a straight meniscus along this flat surface, and then you have the rivulet up here. And now if your inner corner, distance between inner and outer corner is closer, basically the same thing. But then you start getting down to about 1 capillary length, and then you can see the rivulet comes down, then you get separation, and this part here is enlarged. Or here, you're down even closer, less than one capillary length, and you get this separation, what we're calling it. So it gets pinned on the corner, and then the cusp is, you don't see it, it's pinned on the corner. Okay, so this is now looking from the cusp point of view. So the cusp is always at 0 in that case. This is the other way around. This is looking at the rivulet. So here the cusp is here, and the rivulet, you know, is way over here. And now you have smaller and smaller distances between the cusp and the rivulet. And what you can see, now we've enlarged the last bit here. Now we're enlarging the rivulet part. It's sort of like putting all of these lines on top of one another. And they all look the same. And except maybe the very last one is a little bit different. But I mean, then you're way under, that's the separation one. So you're again under 1 micron. So 1 capillary length. So what have we learned? Basically, if these two things are farther apart than 1 capillary length, then they don't really influence one another at all. You get below, then you get influence, but not so much on the rivulet. That stays basically the same shape. The rivulet is more or less uninfluenced by the cusp. Okay, and then you have to start saying, okay, now can we, those are our observations in the lab, and then you go back, can we now describe that? And as I say, it's not rocket science, but it's not always easy, but you can imagine here that you have some sort of a Laplace pressure due to the overall curvature of the surface of the liquid, and that's then balancing hydrostatic, so rho GH. And so you basically have to, and then you can imagine that here, the curvature, if it were straight at the corner and you had a 90 degree, then you have infinite curvature, and then you have, of course, infinite pressure, which you can't have. And so that's why you get a cusp. The cusp resolves that problem, and so that you don't get infinite curvature. That's why you get a cusp. Okay, but you can imagine that the curvature at any one point is not easy to solve. You have, of course, surface evolver you can use, but that also is not always reliable in all cases. But we put a fairly simple model together where we said, okay, we'll take the curvature. We have some C max, which is the lowest we achieve there. And we then say, okay, how can we estimate the curvature in this region here? And we estimate the curvature by looking retroactively. We look back. We solve then for the rivulet, and we know the curvature of the rivulet at that point, and we say, okay, we know the curvature at that point, even when it gets closer and closer, the outer and inner corners, and we use that curvature here to adjust then the Cmax, and we can see then as the step size, this is now short, very short together, and this gives us then a rather good agreement with our observations. So very simple, it's just the pressure, Laplace pressure balanced with rho GH. Okay, this is not too complicated, it seems to work. And then we say that's the cusp side. Let's look at the rivulet side. So there are several models for that, and we can think about two curvatures. Think of a rivulet going up into the corner, and you can think of two curvatures. One is we call the horizontal curvature. So if you had a horizontal plane, then there's a horizontal curvature, but there's also a vertical curvature. That's the curvature of the rivulet going up. And of course, we have to consider both curvatures when we look at the Laplace pressure. And so there are several models, of course, going on to do that. And I've put them here. And so let's just look, first of all, this prediction of the rivulet shape, and you can see I've put several I didn't mention, several additional models with correction factors. And we have what we call a unified equation. It's not completely correct. On the next slide, I show the complete equation. And this, again, is a little bit complicated, and maybe you can see it or just imagine what we're doing from this picture. So basically, from this picture, what we're doing is we're trying to get the curvature normal to the vertical profile of the rivulet. Okay, so as I say, a lot of trigonometry, and this is what comes out in terms of height as a function of where you are along the rivulet. But one thing you can see is that our experimental work, even with our unified theory, is not exactly correct. Part of that has to do with uncertainties, a few things that you don't know exactly, and part of it has to do with a correction we then added, and that is the correction. It's actually not coming from us. But what you can then do is to say, okay, you can look at the rivulet shape with different contact angles. And this is something that some of the existing theories cannot handle, larger contact angles. And that's, let's say, maybe one of the novel features of what we've done. Okay, so it's a little bit, but it's all, as I say, trigonometry in the end. The other thing is that you can look at the speed, the capillary number, so the speed at which the rivulet rises. And what you can see is basically that is unaffected. This is with dimensionless time. So at the beginning, it's moving faster, and as it goes higher and higher and higher, it's moving slower. And if it was a perfect corner, it would go to infinity. And you can see that it's basically unaffected by where the outer corner is until the outer corner gets less than 1 capillary length towards the inner corner, and then we start getting different speeds. So that, in fact, is an effect. The shape of the rivulet doesn't change much, but its speed slows down. And that's something then we also were able to model. That's my highlight from part 1. We had 3 parts, remember? That's part 1. And those are kind of the highlights. I won't repeat them here. But and the next thing was then on the finite curvature. And when I say finite curvature, again, the real world corner, you know, if it's not exactly 90 degrees. And this is now some work. These are some of our experiments with different fluid mixtures. And the 1/3 law is here. So this is coming from our friend in the 3rd row here. And this is, you can see, it agrees very well. This is logarithmic, by the way. And at the beginning, there's some small change, and that has nothing, that is simply we take our sample, and when it first hits the fluid, okay, there's some adjustment, it starts. So, okay, it's not yet sort of steady state. But over most of the time, it's fine. But then we notice that it deviates. It deviates from this 1/3 law, and it doesn't go to infinity, by the way. And we say, okay, why does it deviate? I thought at first we thought, okay, it's just sort of, and it's not easy to do, by the way, because this is a long time, it's a long way up, and so you have to have a very long, as I say, it's not a simple experiment. Okay, and so we did that, and we started thinking about what's happening up here, and we came at, well, maybe it's not exactly 90 degrees, and maybe that makes a difference. So let's go. This is now a theory we come up with. That's the final result. I'll have a few slides with a few intermediate equations now, but that's the final equation we come up. So it's not exactly a 1/3 law, but there's some correction to it. So this is the 1/3 law, and this is now dimensionless time. And this part here, so dimensionless time, up to this point here, that's there. So we're looking at really long times now in this picture. And our new theory agrees fairly well with everything we've measured up to now. And it looks a little bit complicated, but I can assure you that it's, this now is sort of the background of the theory, and I'm not trying to go through all derivation steps of this theory in front of you, but just to give you some idea that our real world corner is characterized by some small radius here of the wall. And you can imagine that if you had a rivulet that went to infinity, in a perfectly 90-degree corner, then eventually when you get higher and higher and higher, the rivulet is so small, the radius of curvature is extremely small, the pressure is then much higher, and that's what drives it up, of course. But of course, the radius can never get smaller than the real world corner. So you've got a limiting factor. And so you have to work out, okay, when does it then stop? And so you start, making pictures like this. And of course, up at the top of the rivulet, you don't have to worry about this curvature anymore because that's more or less straight. You really only have to worry about the horizontal curvature is what we talked about. Okay, so you start working out, then you've got lots of equations, and as I say, you can put them down. It's basic an evolution equation, mass and axial momentum, and we account for some viscous stresses, no inertial effects. Everything is so slow you can forget inertial effects, but you have capillary and gravity, and so you actually get a similarity solution to the differential equation that and you have a factor that comes out of that solving the differential equation. And so you come up with this equation, and you'll see that in these dimensionless numbers, there's this one value here, but there's also sitting in here two factors, a b and this radius, sorry, sometimes it's large r and sometimes it's small r, but that's this actual radius of curvature. So now you have a problem. You've gone to the machine shop, if you've gone somewhere to have your corners manufactured, and then you have to know the actual radius of curvature, and how do you measure that? That's not easy. Okay, on the other hand, you can estimate it, but in fact, the theory works very well. You fit the r and the b to what you've observed, and then you know the r. Okay, so actually what we have is a measuring technique for a radius of curvature in a corner. Okay, this is a little bit backwards. That's not exactly why we wanted to do this experiment, but, and in fact that works. So that's, this is all using, we use the same sample. So we know for the different fluids, the radius of curvature is the same. And in fact, for all three cases, we use the same values of those numbers, and we get good agreement. And then we go, and we can say, okay, if we change the radius of curvature in the corner, how would the rivulet evolvement change? Here I've left it in seconds and height. And not only that, then we can go to data out from the literature, in this case from Deng et al., and we can then fit our model to their data and then tell them what their radius of curvature was, which they didn't know, of course. They didn't think about that. Okay, so actually it turns out that everything fits well together. Okay, and this is from their data. This is the radius of curvature. That's their radius of curvature and the corner angle that they used. They had different corner angles. So, and we can then retroactively find out what experiment they were really doing, so the boundary conditions of their experiment. And now I come, that's my highlights of that part. And now I come to the last part of the talk. And make sure I'm in time, 7.5 minutes. And the last part of the talk is now our sample is going down. So we have forced wetting now. And actually, we call this rivulets of finite height. And the reason we do that is because there's two reasons you can have finite height. One reason is if the sample is going down and the rivet's trying to go up and they cancel out, then it ends up being a finite height and it doesn't go up to infinity, of course. That's one reason. And the other reason is if you don't fulfill this Conkes-Finn criteria, then it doesn't go to infinity and it stops somewhere. And so we have, that's what we call spontaneous finite height, and this is the forced wetting finite height. So you have two situations where a rivulet doesn't go to infinity, and we can look at both, and the model that I'm going to show you actually encompasses both cases at once. And so we'll talk about first the spontaneous case, and again, trigonometry hour. Get out your CRC handbook. And so again, you have to start thinking you have, this red line is sort of the vertical curvature, and the green lines are some sort of a horizontal curvature. And so you can say you have two curvatures, so you get some Laplace pressure, and that has to somehow, it's very simple hydrostatics because nothing much is moving right now. Okay, but this now becomes more complicated than you think, and I will try and explain why. Well, take a look. So this is now the case. We have a corner, and that red is the bisector of the corner. So I didn't show the other half of the corner, but it's symmetric. You just mirror it around the red line. And so you have a case here with a small contact angle, and the radius of curvature is outwards here, that's this r. Then you have a case here with a larger contact angle, and the radius of curvature is now inside. And then you have even a smaller, so another contact angle somewhere in between, and the radius of curvature even outside of the corner. And you think, oh, okay, those are three cases. Those are the three cases I have to deal with. Wait a minute. That's fluid here and gas here. And what would happen if you had fluid outside and gas inside? Then you also have a gas rivulet. And then you have another three cases where, again, the radius of curvature is here, the radius of curvature is inside, or the radius of curvature is outside. So actually, our model takes care of all of those 6 cases. And I mean, these are a little hypothetical, but they also occur, you know. So you would have actually external wetting. It wouldn't be in the wetting wouldn't be in the corner; it would be outside of the corner. Okay, so and now you can see what we're doing is we're now taking. It's not exactly. I mean, here's the vertical curvature, and the horizontal curvature is not really what you want. What you want is the curvature normal to the local vertical curvature. And that's what we've tried to show with this green triangle here, or here. So this is now normal to the red line. And those are the two orthogonal curvatures that go into the Laplace equation. And okay, so this is, again, you have to start doing all kinds of triangles and whatnot. And this keeps you busy. And okay, so this is, I won't try and go through it all, but this is a little bit what we're saying. At some point here, we now want normal to that, the curvature in the other direction. It's not horizontal, it's not vertical, but it's somewhere in between. And that in between is the alpha, and this alpha is, I think I showed somewhere here, well, I have alpha somewhere, you can work out what alpha is. And then you go into your equations, depending on whether alpha is larger or smaller than 0. Again, that's the convex or the concave case, although we cover all cases. And then you can start saying, okay, and how about the contact angle? And again, this is now all contact angles. This would be, it's not restricted to the Concas-Finn criteria. And so you can then look at dimensionless height against dimensionless length and look at the effect of different contact angles. Okay, and then the question is, does it agree with what we measure? And so we can take a look at the red line. That's our model. We call it a 1D model, and because we're just hydrostatic, and our experiment lies here. This is what we got with surface evolver, which is also rather, again, sensitive to some of the contact angle and boundary conditions. Okay. That's actually the story, and it seems to work. But now let's go and look at the final part, and that is now, that was the spontaneous finite rivulet rise. Now we look at the forced finite rivulet rise. So now we have a fluid, the specimen, the walls are going down. And basically what it's a fairly simple assumption we're making. We're saying, if the rivulet was rising on a stationary wall, and it came to some height, and at that height, it has a certain curvature, then we would say, okay, put that to side, and now have the wall coming down, and the rivulet has some stationary height with the wall coming down. And at the same height, it has then basically the same forces acting on it, because it's going up with some speed. So if it's at some speed at that height, and the wall is going with the same speed down and it has the same height, okay, then the wall shear stress is exactly the same. So we have the case, this is the stationary case, and the rivulet's going up, so you have some viscous force on the wall, so no slip condition, so you have some wall shear stress here. And now we compare that when the wall is going down, and we get the same height here, then the wall shear stress is the same. The outer boundary condition is, of course, no shear. Here we have mass flux 0. Here we have mass flux mean velocity over the height. Okay, so now comes the tricky part. Actually, that's all you need. You solve the equation now for the height here, because you know the rivulet rise You know how that we've solved before. And so you now just solve for the height. It's actually trivial now. And so you can actually get, so you know the 1/3 power law. You know how the rivulet's going up with time. So you know all of that, and you just equate the two cases. And you get then this red line, and those are dots, are the experiment, and this is this 1D model that we made, and it agrees fairly well. Then you can see we don't have any, that's time's up, I have to stop. But this is almost the last slide, so I think it is the last slide. So, we don't get any more dots here. Why? Because at the very, very low capillary numbers, it goes up so high that it goes out of view of the camera. And we don't have any more dots down here because at the fast, then what happens, of course, two things happen. First of all, you hit the bottom of the pool. Or the other thing that happens is that, of course, eventually the rivulet becomes flat. And then you can't see it anymore. It gets negative. So, as I say, it's a difficult experiment. Okay, so, but in the region where we measured, it seems to agree well. So this is basically, this is this very simple equation of those two cases where you get then the height of the rivulet for a given velocity. The Q is a number you have to get from experiment, but you do that on the stationary case. You get the Q and then you know it, and that's the end. Those are the highlights. Thank you very much for your attention, and those are the people who paid for it. That was an experiment, and that's the lesson you learn. Make sure you have your talk finished before you get on the plane.
Great, so thanks a lot for this talk. Really appreciated it. I'm thinking about this second part of the talk where we have the slight curvature at the inside of this maybe 90 degree.
Finite curvature, yeah.
Right. This makes perfect sense. My question is, it seems like for a real fluid, even if we have the perfect 90 degree scenario, we might still have some limited rise height due to some evaporation. So is that something that's on your...
So you might have some what?
Some finite rise height due to some evaporation of the fluid from the surface. Yeah. So you might have some pressure drop due to the flow that's used to then replenish due to the evaporation. Yeah. Is that something that's been on your mind or that might come into play in the experiments here?
No, actually, no, we never got to that point. I mean, it was, we're a little more macroscopic in that case. But the silicone oil has, you know, it was just not evaporating. So this is, I don't think it's a problem in our case. But yeah, I guess you could imagine where you have some thermal effects and thermocapillary effects there, yeah. But in our case, I think, one reason was the silicone oil was basically almost, I mean, you have problems in machining. You machine and you have little, so we had the silicone oil, basically, it never pins, it's always wetting. This is a problem, yeah. But the evaporation we didn't look at.
Thank you.
So David, you must have a question, David, because he's been cited so often in this talk that it.
Oh, sorry. So the cusp thing. So it's a wetting liquid. However, because of geometry, it becomes somehow non-wetting in the cusp region. You have a meniscus which is pointing downwards.
Yeah, I'm not hearing properly.
Is it better? Okay. So I was saying the cusp is something which is created by geometry. So it's a wetting liquid that becomes geometrically non-wetting, in a sense, because your meniscus is going down. And so if you push your object on the minus z direction, do you entrain air, for instance, along the corner?
Yeah, I can add, you know what? We didn't look at the cusp under the forced wetting case. But yeah, it's an interesting, that's what you're asking, on the outer corner.
Yeah, exactly.
And you're moving down. We never looked at that part.
Yeah.
That's, the guy was finished his PhD and... But yeah, it would be interesting. But the other interesting thing is, of course, and this is what I didn't show. I actually missed that last slide. I should have shown it. Is as you go faster and faster, of course, you get a cusp going down, and we can't see that with our imaging equipment, and so we didn't look at that. But you have to understand, and maybe if it's allowable, I think I had another picture here. And the other picture, there's three things here. One is, okay, influence of roughness on the wetting. And the second thing was it would be nice to measure the contact angles. And I think we can do that now with this free wavelength interferometer. And the third thing is, if the cusp is not up like this but down like this, then you have basically almost straight meniscus. And we used the Kistler model for the dynamic contact angle, by the way. And because it's moving, you see. So we had to put in a contact angle, and we had a dynamic contact angle. But if the cusp is up like this, then you have that basically the solid is moving like you have an oblique wetting front, and who knows whether the Kistler dynamic contact angle is valid for an oblique wetting front. We don't know that. We know for a normal wetting front, we have several models, but for an oblique we don't. And so those are some of the open questions we saw. But how the cusp behaves going down, I don't know. Sorry.
Yeah, one small question. So you have done it on millimetric scale kind of structures. So how would this, let's say I'm changing the structure to micrometer kind of scale, a smaller version of this, let's say.
What number?
The structure which you have created, which is in the millimetric scale, I guess.
Yeah.
So if I make it to the micrometric scale, how would this would behave, the rise?
Well, I think we shouldn't talk about units, in meters. We should talk about capillary lengths. And so I mean, it's clear you got down to micrometers and you're much smaller than a capillary length, which was 1 point something here, and millimeters. So I mean, there you could see there's a huge influence between cusp and rivulet. Okay. And so I think at very small scales, everything changes, yeah. That's why I said I'm really only tangential to this audience. We're capillary lengths and larger. Sorry.
Okay. And also regarding that, because of the corner roundedness, you are seeing a lower rivulet rise, right? So do the bulk liquid also show a much higher level of increase or rise when the roundedness of the corner increases?
I didn't understand the question. Did you understand?
When the corner get more rounded, the curvature of or the roundedness of the sharp,
roughness.
Yeah, means the sharp corner getting rounded.
Yeah.
It is actually causing the rise to lower, the rivulet rise to get lower.
Yeah.
So do you see at the same time, do you see the bulk liquid would also show an increase in rise?
Well, I showed that. That was the rivulet contour. And that changes with the radius of curvature. I think I showed that also. Maybe I only showed the contact angle effect, but you can work that out with the equation. You get the contour, then yeah, it comes out. So yeah, how does the contour change with the corner R? I think I don't have a graph in my, but this is something you can compute now. The model works, is what I'm saying. So yeah, sorry, I can't.
Thank you.
Show you something immediately. Yeah. So Demos. Yeah.
Thanks, Cam. That was a very nice talk. I think I was covered partially by David's question, but I mean, you didn't look into this wetting problem in detail, right? You know, how the wetting takes place. Because my question would be if you could reach this by playing with the wetting going the other direction now for phobic.
So de-wetting.
An anti-rivulet.
Yeah.
Anti-rivulet that you entrain the air, and then the non-wetting behavior will help you in that way.
Yeah.
And you can see it from the back. We can use transparent surfaces and see it, actually. Yeah.
Yeah. Well, yeah, I mean, we do a lot of wetting experiments, and what we've done here is, of course, we're only looking at the advancing contact angle, and most of it was done at such a slow speed that we're looking at sort of the static advancing contact angle. But with the forced wetting, we went to a dynamic advancing contact angle model, and we used the Kistler model, which seemed to be. But those are the uncertainties, of course. Even the contact angles we were putting is, well, you know Robin Ross, it's plus minus 5 degrees or something. And we're living with that uncertainty, yeah. Mm-hmm. No question, yeah. But that's why this interferometer would be so great. Because then you could measure the contact angle online and time resolved without a reference, because it's 3 wavelength, yeah.
Hello, sir. My question is, if I take a rough specimen, textured surface, and deep in the fluid, then three-phase contact line motion of fluid and wall surface will pinned. Then what will be effect of textured surface?
Yeah, yeah. Okay, this. Everybody's asking questions I can't really answer. Okay, but it's fairly clear that the roughness, of course, this is now a question of wetting. It comes back also a little bit in the direction of what Dimos says. The wetting, of course, on a rough surface is completely different, and you'll get pinning. And that's why we use silicone oil on stainless steel or on aluminum. It basically wets everything. Even if there's little roughnesses, machining, it just wets it. But you're right. I mean, if you have, if you're going into paint and it's a rough surface, then it will pin on roughness elements, and then you'll get sort of a stick-slip behavior, and then I don't think a lot of what we do will apply. I think, yeah, this is almost too practical.
Okay, with that, we'll thank Professor Tropea and small token of appreciation.
Okay. Thanks so much. Yeah.